Hi students, in today's video class we will be studying about basic assembler functions. That we will be studying is what are assemblers and how it is used in SIC machines and SIC XC machines here. So this is module 1 lesson 5. Outline in today's class is a simple SIC assembler algorithms and data structures used in assemblers. So what is assembler? An assembler is a software program or a system software that converts assembly language into machine language or machine code. It takes the basic command and operations from assembly code and converts them into a binary code that can be recognized by a specific type of processor. So that is nothing but your assembler, which converts a assembly language into a machine code. So as you can see in the diagram, a source program is given to the assembler, and what assembler does is it converts that source program into object code, which is nothing but your machine code, which is understood by the machine, and it is given to the linker. Linker is used to link some other subprograms to the main programs. Then an executable file or executable code is generated and is given to the loader to load in your system. So that is the role of a assembler. So assembler also does two functions. It converts the mnemonic operations codes into their machine language equivalent, and also it converts symbolic labels into their machine address. So next we will be seeing what are assembler directives of SIC machine. Start is nothing but your assembler directives. So it can be used in your program. As you can see, it is used in a code snippet which I showed in the slide. Start is nothing but it to specify the name of the code and the starting address of that code or a program. So start, it means it says the name of the program is copy and the starting address is nothing but 1000 there. So one more example of assembly directive is end. It indicates it is the end of the source program and specify the first executable instruction in the program. So it also specifies the first instructions to be executed in the whole program. That is first line is nothing but your fifth line, which is that copy start 1000 is nothing but first line. It has to be executed first. So it also specifies that. And one more directive is byte. Generate character or hexadecimal constant occupying as many bytes as needed to represent the constant. So if you want to generate or a character or a constant, we can use this byte. Word, it is used to generate one word integer constant. Then RESB, that is reserved byte. It's used to indicate number of bytes for a data area. For example, as you can see in the code snippet, line number 105 RESB 4096. So that is nothing but your binary number that will be converted into a hexadecimal number, which will be nothing but your 1000. That means your 1000 bytes are reserved for the next instruction. Okay, so that is the use of RESB, the reserved byte, or you can say reserved word in your line number 100. That means one length or one word is reserved for the next instruction or for a data area or for the any other uninitialized constant here. So next we will see about data structures used in assembler. So there are three data structures used in assembler. That is op tab, that is operation code table, sim tab or symbol table, location counter, that is location counter table. 3 data structures are used. As you can see in the diagram, there are pass1 and there is pass2. That means there is one pass1 assembler and a pass2 assembler. Both assemblers are used together to generate an object code. So why it is used pass1 and pass2, why not only one assembler here? We'll see that in later videos. Right now, just see, we'll see today about data structures, only op table, symbol table and location counter. Firstly, why op table, operation code table is used? So what are the contents used in that operation code table? First one is mnemonic operation codes used in the program that will be stored. Next is machine language equivalent, and next is instruction format and the length of the instructions will be stored in the operation code table. Then why it is used? During pass 1, it validates operation codes and it finds the instruction length to increase the location counter value. So it also finds the length of the instruction so that we can increase the location counter value. Suppose it is a 2 byte or a 4 byte, depending on that instruction length, we can increase the counter value. Then it is also used, as you can see in the diagram, it's also used in pass 1, it's also used in pass 2. So it is used in pass to determine the instruction format. What kind of instruction format it is? Is it 3 or 4? And also it translates the operation codes to their machine language equivalents. So implementation, implementation used in the op table is, it used hash table because it's easy for searching. Hash tables are easy for searching, so that implementation is used in op table. Next is symbol table. So contents in the symbol table is, it contains label name, name given to the instruction and the label address. Then it contains flags to indicate error conditions. If any error condition occur in an instruction given, it indicates that error also in a flag. And it contains the data type or a length, and it is used during pass 1 and pass 2 also. So why it is used during pass 1 assembler is, it stores label name and assigned address in a symbol table. And during pass 2, symbols used as operands are looked up in symbol table. So that is the use of your symbol table. During pass 1, what is that? It is stored the label name and some assigned address. Then during pass 2, symbols used as operands in the lookup table here. So if you want to retrieve the operands, we can search in the symbol table for that, because the label name and the address are stored in the symbol table during pass 1. And implementation, how it is implemented, implementation is, it is using a dynamic hash table here. During op table we use static, in symbol table we are using dynamic hash table for efficient insertion and retrieval, and it is also perform well with non-random keys here. So that is the use of dynamic hash table. So next we will see about location counter variable or location counter data structure. So variable accumulated for address assignment is location counter, gives the address of the associated labels. So variable accumulated for address assignment, it gives the address of the associated labels. What address is needed for the labels, it gives that address. So location counter is initialized to be the beginning address specified in the start statement. So firstly, your location counter, because your location counter consists of what? It consists of the addresses. So firstly, your location counter will be initialized with the first address, starting address you can say, which is indicated by the start symbol or start directive. In the previous example we have seen start 1000, that is a starting address. So that is initialized in your location counter here. After each source statement is processed during pass 1, the instruction length or data area is added to the location counter. So that is the use of your or that is used in your assembler pass 1 and pass 2. As you can see in the diagram, location counter is only used during pass 1 because during pass 1 only the addresses are stored or addresses are retrieved or what you can say collected during location counter. Okay students, in next we'll see SIC assembly language program. Example given in your textbook, where we need to find out the object code for the given code here. So code is written in an assembly language and we need to find out the object code here of that program. So the first column indicates it's a line number, and the second column indicates it's a label name or anything like that, label, and the third column is nothing but the opcode, and next column is operand, and the last column is comments, what it is, instruction, comments. Now what is label? In the second column you can see copy, first, C loop, end fill, end of file, E of F, 3, 0, all those is nothing but are labels. Now what are labels? A label is an identifies an optional labels. So it is can be optional also, are used to reduce reliable upon programmers remembering where data or code is located. The length of the label differs between assemblers. So it can be optional. If you want you can use it. It depends on the programmers why they use it, because they can remember the where the data is stored or a code is stored or where the code is located here. So next, opcode. Opcode is a machine code instruction. It may require additional information like operands. Opcode might be example like compare, rsub are called as operators. So compare 0 is nothing but a opcode here. It is with operand. Compare 0 is in line number 25. It is also a opcode with the operand, and there can be opcode without operand also. For example, at line number 75, rsub, return to subroutine. So it will return to some caller or a subroutine. It doesn't require any operands. So this is the example of your opcodes. Next will be operands. So it is an additional data or information that the opcode requires. Operands are used to specify constants, labels, immediate data, data contained in another registers, and it can be address also, etc. So this program contains a main function calls the subroutine RDREC to read a record. You can see in line number 50 to read a record into a buffer, and subroutine WRREC to write a record from the buffer to the output device. So that is the main function of this given program. So each subroutine transfers record one character at a time, because only input output instructions available are read and write here. Since the input output nodes of two device may be different, a buffer is used. End of each record is marked with null character, that is 00. If the record is longer than the length of the buffer, then only the first 4000 2096 bytes are copied. The end of the file to be copied is indicated by a 0 length record. The program indicates end of file on output device when the 0 length record is detected. The program terminates by executing R subroutine, that is R sub instructions, since it was called by J sub instruction. So, next we will see how to generate an object code for the given example. So, before that we need to understand that in the second column location counter and the object code are generated. So, remember one thing, location counter is generated during pass 1 of the assembler and the object code is generated during pass 2 of the assembler. So, location counter, you can see it stores the address of all the instructions and then the object code will be generated. Why? Because during the pass 1 or during the first stage we need to know what is the starting address of each instructions. So, after you get to know the addresses, we can generate an object code during pass 2 of the assembler. Okay. Now, we will see how to generate this location counter or the addresses of each instructions. So, as you can see, the first instruction start 1000, that means it indicates that the first address of the instruction should start from 1000. So, line number 10 it says that first instruction is 1000. So, it will be started with 1000. Now, as I told you before, your SIC machine will be having instruction length of 3 bytes, that is nothing but your 24 bit. So, each instruction will be having of contains 3 bytes. So, all each addresses will be adding 3 bytes for each instruction here. For example, 1000. For next instruction, the location counter will be incremented by 3, that means 1003. So, next instruction will be added by 3 again for each instruction, because all the instruction will be having the address length or instruction length of 3 bytes. So, 1006, 1009, again for 1009 plus 3 will be added, it will be 1000C, because 9 plus 3 will become 12. So, as you know, it is a hexadecimal numbers. So, A means 10, B means 11 and 12 means C. So, 1000C. So on this values will be incremented. So, remember one thing. So, during assembler directives, for example, reserve word, reserve byte, we need to be very careful while incrementing the location counter. So, as you can see at the line number 95, reserve word, that means they have given 1, reserve 1 word. 1 word consists of 3 bytes, that means 3 will be incremented, 3 bytes will be added to the location counter. So, if for example, if they had given reserve word 2, it means we need to increment 6 bytes for that location counter, right. So, that is something we need to remember while incrementing the location counter. Next, you can see in 105 line number, reserve byte of for 4096. We need to reserve some bytes for some memory or for some constant for uninitialized variable, that is 4096. Now, that 4096 is in a binary number, the decimal number. That decimal number should be converted into a hexadecimal number. So, if you convert that into a hexadecimal, you will get 1000, that is 1000. That means 1000 bytes of memory should be reserved for this directive, that is your assembler directive here. So, you have to be very careful while allocating this addresses while we have assembler directives. So, as you can see here, 1000 bytes are reserved for that instruction. So, next instruction will be starting from 2039. Okay. So, we'll see how this object code will be generated. As we have generated all the location counter values, now we'll see how this object code will be generating for each instruction at the column number, the last column object code. So as you can see in the diagram or a code snippet, line number 10, we need to find the object code for that. So as you know, the instruction format for SIC machine is first 8 bit will be of for the opcode, next 1 bit is for X, for is it index addressing or indirect addressing, indicates that, and the next 15 bits will be for the address. That was the instruction format which I already told you in the previous videos. Now in opcode field is nothing but your opcode here is nothing but your STL. So STL value opcode, if you have search in your textbook, you will get opcode value is 14. So that will be stored in that 8 bit opcode format. So 14 will be stored as like 1 0 0 0 0 1, then 4 will be stored as 0 0 0 1 0 0, that will be stored in your opcode field. Then next is X. X will be 0 because the statement or a instruction is not a index addressing. If it is a index addressing, if it will be like comma X. That time we will get to know that is it indirect addressing or a index addressing. Okay, so right now it is not index, it is indirect addressing. So value of X will be 0 here. Next, the address field. So what is address field here? The operand here is return address. As you can see in line number 10, return address, RETADR, that is nothing but your operand value. So what is the address of that return address? Is nothing but at line number 95 you can see the location is nothing but 1033. So that is nothing but the address of the RETADR, the operand value. So that value will be stored in the address field of 15 bits. Now already I told you in opcode field 14 will be stored, that is in the form of a binary number, then X value is 0, then in 15 bit address value this address will be stored, which is nothing but your hexadecimal number, that is 1033. That will be converted into a binary number, that is for 1 will be stored like 4 bit 0, what is that 0001, then for 0 again 000, for 3 it will be again 00011, again 0011, that will be stored as a binary format there. But remember, as you can see there are 4 digits 1033, that means for each digit we need 4 bits, but there is only 15 bits in your address field. So remember, if you want to store that 16 bit into a 15 bit address field, we need to discard the leftmost bit of that address. You need to discard the leftmost bit to store that address in that address field, not the rightmost, not anything like that. We need to discard the leftmost bit. So what will be stored in that address is nothing but 001, because 1 is there. Next we have 4 zeros. Next for 3 will be having 0011, again for 3 will be having 0011. So if you calculate all the full binary number, what we will be getting is 141033 as the object code. If we convert that again into a hexadecimal number, you will be getting 141033 as your object code. So that is nothing but your object code for your line number 10. Next again you can see in line number 15, jump subroutine RDREC. Jump subroutine also is a opcode of a job subroutine will be 48. They'll give you the object code for not object code, the operand opcode for each instruction. In your textbook also you have, and during exams also, if they have given you code snippet, they'll give you the opcode value. So opcode value of JSUB is nothing but your 48, and the return address or a return record REC is nothing but 10 return address 2039. See here 203, this is a continuation part of that program. Return read record 2039 is nothing but the address of that field. So the same thing if you add convert that into a binary number, and again it is not a index addressing. So again the x value will be 0, and same thing the address will be stored into a binary number and will be added together to form a hexadecimal number. So again it will be 48 2039. Okay. So in the next continuation part of the program, you can see at line number 160, switch to buffer comma x. That means now that instruction is nothing but a indexed addressing. That means your instruction format, that format I told, that x value will become 1 now. So STCH, the instruction opcode value is 54 and x value will be 1 now, and the address of the buffer, what is the address of the buffer? Address of the buffer is 1039. You can see in the diagram there at line number 105, 1039 is a buffer address. Now how to calculate the object code for that line now, 160 line. So 54 is the STH opcode. So 54 will be converted into a binary number, x value is 1, and 1039 will be also converted into a binary number, and it will be stored into a 15-bit number. Remember, it is a 16-bit, but we have to store into 15-bit, discarding the last digit. So your what is that, 900 last rightmost digit, digit is nothing but your 9 will be same as 9, 3 will be same as 3 there, and 0 will be same as 0. Then your x bit 1 and the last 3 digit which was discarded, 1 was discarded and the last 3 digits was remained there, 1001. 1001 becomes 9. That means 549039 will become the object code of that given instruction. So at line number 185 you can see byte here is nothing but your assembler directive xf1. So xf1 is a operand here. It means it says it's a hexadecimal value. It is a direct hexadecimal value. So if it is a hexadecimal value, directly it is stored in your object code here. Similarly word, next line 190, next line word 4096, it is a decimal value and it is converted into hexadecimal value and stored like 1000. Already you have seen 4096 will be converted into a hexadecimal value, that is 1000, and it is stored in your object code. One more thing I forgot to tell you is at line number 80 and line number 80 end of file, that is byte is assembler directive. So it is of character type EOF. So the what is the hexadecimal value of EOF, that will be stored in the object code. E, the hexadecimal value is 45, O, the hexadecimal value is 4F, and for F it is 46. So that will be stored in the object code. I hope you understood this code snippet of assembler as SIC assembler. So in next video we'll be seeing about SIC XC assembler, the object code with the example. So thank you so much.